today is going to be the theoretical approach, and the next day I will ask you to bring your laptops. I see everybody has a laptop except you, but the next day you should have a laptop here, because we are going to code the variational autoencoder ourselves. Okay, but let me do. Is it recording already? Let me do one thing. It's going to be odd, like now, just to match audio and video. Okay, so do we have something to pass the slides? Okay, I will start with some introduction. Today we are going to talk about generative models, which are a kind of deep learning or artificial intelligence models that are very common these days, because these are the ones that are able to generate new data out of almost nothing. Probably you know ChatGPT, or you know DALL-E, Stable Diffusion, these ones that can create out of a prompt some images that are completely novel. So these are what we are going to study today. What are the foundations of this kind of models? And specifically, because there exist a lot of them out there, we are going to talk about the variational autoencoder, which is a specific model. This is the overview for today. First, we are going to talk about the review of some artificial intelligence concepts that I think you are aware of some of them. Learning paradigms, they are going to be just as a review. We are going to be quick on that. Then maybe this one you don't know, the discriminative versus the generative models. And then we are going to take a look at the taxonomy of the generative models, which generative models exist out there, and why we are choosing the variational autoencoder. Then we are going to talk about some audio concepts. Probably you're also aware of this. Very simple. We are going to work with some spectrograms, some raw representation of the audio. Then we are going to head the variational autoencoder. But variational autoencoder has two names, two particles in its name, variational and autoencoder. So first we are going to understand what an autoencoder is, and then we are going to understand why we set the variational word to the autoencoder. Good?
Just to mention that the slides and all the materials are in Moodle.
Yes, the slides are they already in Moodle? Okay, because these are different. Then it's not the same as this last year, but don't worry, because I will upload this and the video. I will upload the video and you can check it whenever you want. So not working. Do I need some? Yeah, sorry. Okay, so the review of the artificial intelligence concepts. First of all, what is the supervised learning? You know about this. This is again what probably you have heard about this, but let's have a quick recap. So what we have in supervised learning is some input data. Okay, X is the data, and it's going to be X. It's going to be the data for the rest of the lesson, and Y is going to be the label. And the goal is to map X to Y to have some kind of function or some kind of model that is able to map X to Y. So if I tell you that whenever we have a 1, we receive a 2. Whenever we have a 2, we receive a 4. Whenever we have a 6, we receive a 12. Our model should be able to predict what we will have if we input some other number like a 10. Of course, it will receive a 20 because it's multiplying by 2. So what we are doing in supervised learning is that we are generalizing knowledge. We want our models to generalize to some data that is not labeled, so we can generate a label. Okay, this is a very simple example. We can use it for classification. We can use it for regression, object detection, semantic segmentation, captioning. Another example. This is very typical because it was like one of the first applications that worked with supervised learning is to be able to detect spam emails. And it's something that as humans we can do, but can you tell why an email is spam, whether an email is spam or not? I mean, you can do it, but what are the reasons why you consider an email spam? That's more difficult to code, right? And that's what an artificial intelligence is able to do. So that's amazing, actually. And some other applications, even more difficult. For example, I'm thinking about one that was able to predict if somebody was suffering from depression based on their Instagram posts. I mean, and they were more accurate than actual experts, right? So this is supervised learning has been like the hot topic these days. But until last year, in which the most important learning is the unsupervised learning, in which we don't have any labels. We just throw to the model all kind of data that we may find out there on the internet. And the goal is to learn some information, some underlying info that is in itself inside of the data. So what we are doing is inferring knowledge. And one example that I'd like is that if I showed you these images, and they don't have any label, right? But you have some knowledge about them. You know that this is The Simpsons, and you know this is Griffins, or you may know that this is old people, and this is teenagers, or they are male, and these are female, right? This information is in the data, and this is what the unsupervised learning is learning. So based on the data in itself, it's inferring some knowledge. Some other examples. This is the same clustering and very typical algorithm, the k-means, right? Or the PCA. You know about PCA, principal component analysis? No? Yes? This is the dimensionality reduction. So what we are trying to do in this kind of unsupervised approach is if we have some information with some dimensions, and some of these dimensions may not be relevant, may be redundant, or we just need to compress them in an efficient way, we may apply this algorithm and convert data that in the beginning was 3D to 2D. And still we know we still can clusterize, right? So we have done it in an efficient way. Or the feature learning, that is understand what are the characteristics of the images or some data that we may input, and be able to, based on these characteristics, this is also dimensionality reduction, but in a more efficient way than the PCA, be able to reconstruct it. So this is actually what we are going to learn today. This is an autoencoder. Or another important one, the density estimation, in which what we are trying to do with the data is to understand if there exists some underlying probability function, and if that exists, then we may find it, and then we may use this probability function with this density for something. Okay? So this is the first idea that I wanted to mention in the class. Is there any question related to this? I guess this is simple. No question? Okay. Then we are going to jump to a different way of approaching to machine learning algorithms. So we have seen the way in which we approach based on the type of data that we have. It's labeled or if it's not labeled. But now we are going to try to approach in a way that we would like to find some probability distribution that maps some way the information, the training data that we used to train our model. Is that clear what I say? We want to find some distribution to map the data with which we train our model. function distribution, so probability. Now we are thinking about probability distributions. Are you okay with that? Okay, I guess. So depending on the way we are going to map to the training data some distribution, we distinguish 3 different models. So remember, X is our data. Y is our label. So the first model, called the discriminative model, is trying to learn some probability distribution condition that we know X. So we want to learn the probability distribution of the labels condition on the data. And this is closer to the supervised learning, right? In which we try to map some labels to some data. So in this case, we try to learn the distribution that maps those labels to that data. Okay? Then the generative model is trying to learn the probability distribution of the data itself, not the labels at all, just the data. So the probability distribution that defines all the data that we may input to the model, which is infinity. But this can be done. And this is what we are going to learn today. Even though it's an infinity distribution, it doesn't end because we can input any image in the model. We are going to learn to create this probability distribution. And then we can learn a probability distribution that maps condition on what we know, why some input, some prompt, some label, learn this distribution, condition this distribution. And this is exactly what Stable Diffusion does. We condition the generation of images based on some prompt. Okay? So just a quick recap. Whenever we work with probabilities, we usually talk about the mathematical object that we use to define a probability is the density function. You know about the density function is the P of X, right? And every time that we input some data to the P of X, it's going to output how likely this data is in this probability function. Okay, is that clear? And one of the important conditions or one of the important properties is that it always sums up to 1, always, in all its space. And this is an important condition because this is why we need to create different probability distribution, different models because of this condition. And you're going to understand why in a minute. Any question on this point? This is probability. We have studied this in señales aleatorias. Second year. So the discriminative model, the one that we want to learn the probability distribution of Y condition on X. So the probability distribution of the labels condition on the images, supervised learning. It's going to output, if we input Homer Simpson, it's going to output this, for example, this probability distribution, this density, in which the likelihood of being a Simpson, if we inputted Homer Simpson, is higher than being Griffin if we inputted Homer Simpson. This is clear. But the problem is that what happens if we input something that doesn't match the labels that we are considering? Well, because it needs to sum to 1, these bars need to sum to 1. But they doesn't make any sense because we have inputted American Dad and the labels doesn't match American Dad. But it still is outputting some likelihood. So we don't know if this image is okay or not. It could be, I mean, imagine if we have inputted some random image. It still needs to give us some likelihood. It doesn't make any sense. We need to do something to fix this problem of the likelihood. And what we can do is to have a different approach, a generative model, in which we don't have this problem, because while in here the labels were fighting for probability mass, in here the labels are not fighting. The images are fighting for probability mass. So if we are, you need to think of that if we, in this case, we need to have a huge, a deep understanding of the visual world, because we can input any image in here, and it needs to give some likelihood, but it needs to be higher to the likelihood of the images that we had in the training data set. So in this case, an extreme example, like inputting the image of a dog, which doesn't make any sense with the images of cartoons, needs to have low likelihood. And this is exactly what it happens with the generative model. So it rejects random images or outliers. Is this clear? So when we want to have one step forward on the generative model, we can condition it to some label. And what we are doing is that we are modifying the likelihood of the images dependent condition on some label. So if we say that we want to condition our model to the Simpsons, then Homer Simpson should have a higher likelihood, but the rest need to have lower likelihood, including random images. And if the label is Griffins, then Peter Griffin should have a higher likelihood, but still, the image of the dog needs to have low probability, low likelihood. So we, with the generative models, both the conditional and the normal one, we can avoid having random inputs. That's an important characteristic. And now, why it's important to think about models, artificial intelligence models, machine learning models as probabilities or as distributions? Because the distributions can be sampled. And if we sample a distribution, we can get new data. So if we are able to model this distribution, if we know the distribution of all the images in the world, we can create new images that doesn't exist. And these are the basics, the idea of the generative models that are very famous these days. Okay? There's an important property as well, is that we have talked about probability of y condition x, of x, the density function of x condition y. Doesn't this recall to some theorem? Bayes theorem, Bayes rule. That is, if we have trained the discriminative model, and if we have trained the generative model, the conditional generative model is direct. We just need to know the prior over the labels, but this is very simple because this is just summing in the training data set how many labels we have of Homer Simpson, maybe 60%, and the 40% are Griffins. But this is a prior. This is very simple. And we have, if we know if we have this, and if we have this, then we have this. Okay. Any question? I'll let you think about it. So properties, this slide is, we have talked about it, but for you to have. We can assign labels to data with the discriminative models. We can do feature learning. That is, imagine that we have some neural network that computes some classification, and we remove the last layer. Then the new last layer is some features. This is feature learning. Or in the generative model, we can detect outliers. We can do feature learning, but in an unsupervised way. And very important, we can sample new data, generate new data. And in the conditional generative model, we can assign labels while rejecting outliers and generate new condition data. I'm going to open the door. It's very hot. Okay, so just the last slide on this topic of the review of the artificial intelligence concepts is the taxonomy of the generative models. I pasted this for you to have because we are going to talk about only about the variational autoencoder, but the generative models can be divided into models that are able to explicitly learn the density function, and some models that are not able to learn it, but we can still sample from the density function. Okay, this is for you to know. And the one that we are going to learn is the variational autoencoder, which is one that in which we can have the probability function and we can sample from it. Okay, but this probably you will know during the rest of the course. Not sure. Probably you will know about generative adversarial networks. It's not very famous. But today, this is our topic. Okay. Any questions? Okay. Then, now that we know about this, we are going to review some of your concepts before heading to the variational autoencoder. Because what we are going to code the next day is a variational autoencoder that is going to be able to create new audio. That's why. So, this is just about hype of what we are going to learn. Some real examples of generated sounds out there, some different enterprises or different businesses that post in their web apps some models in which you can use them and generate new audio. For example, Fake You is a website. You can go there and generate any audio based on any prompt. For example, I have here, I hope you can listen to it, but it's Bart Simpson saying something. It's in Spanish, but okay, it's quite good. It's very similar. It says, esta voz la ha generado Mateo, literal le ha costado 5 segundos. I mean, you couldn't notice, but it's a bit robotic. And this is because it's trained on Spanish Bart Simpson. Probably we have less samples for that. Or probably the model is not that good. Another one, we can generate music. I'm a big fan of Elvis Presley. And I'm not that big fan that I'm into listening to AI-generated Elvis Presley, but that exists, and you can listen to it. It's quite accurate. Some words doesn't exist, but it's accurate. Another one, for example, I don't know if you like synthesizing music, but some artificial intelligence models help you synthesize music, like this one. I mean, create different different synthesizer plugins and things. Not this. Sorry. Okay, not the voice, but what you can listen in the background. I want to stop. Somewhere in the video, it claims that it was generated by artificial intelligence. Okay, and last one, and this one I don't have any audio, but I like it because the past months I've been working with them because this is some people in the University of London, and they create audio effects also for video games. In case you code video games, you may be interested in what they do. No. Okay. So now to the the important things, right? So whenever we want to input some audio to our artificial models, let's say that we want to train some neural network, we can input the audio as it comes, like the raw audio, that is the waveform. Some deep generators use it, and they are state of the art. But I want to point out the advantages and the challenges of using the raw audio. So first of all, the advantages is that raw audio is raw, so we don't have to do any pre-processing to the audio. Simple, okay? And all the dependencies of the audio are kept because it's raw audio. We can keep the pitch, the melody, tempo, structure, timbre, okay? But the problem is the challenge is the raw audio is massive. It's massive, it's huge. Like well-recorded audio may have in just 1 second 44.1K samples. And that's a lot of samples for just 1 second. Imagine training a recurrent neural network. I mean, it's going to forget what's going on in the some hundred samples before, and that's just milliseconds. So we can't really use it unless we have some different approach, but not directly. This is what exactly I just said. Because we have too many samples, it's difficult to keep long-range dependencies, and because we have too many samples, it's computationally expensive, and because we have too many samples, it's generative. The range generation is slow. So what can we do? We can use spectrograms as the input of the neural networks. Spectrograms can be seen as an image, so we can use the convolutional neural networks to learn the features of the spectrograms. Some of them use it in the state of the art. And what are the advantages? Well, temporal access is more compact, so we don't have this problem of the longer dependencies. So it's easier to capture the longer dependencies because we have less data, less samples. It's computationally lighter, but of course, it's a drawback. Some local patterns may be lost. It's not as accurate as having one sample every 1 millisecond. The phase information is lost. There's no phase here because we usually, even though Fourier transform it's a complex function, we usually take the absolute value. Okay, so phase information is lost. And the reconstruction to the waveform, which is in the end what we want, because we want to listen to it, may be challenging as well. Okay, but still, this is something that you need to know. But we are going to use spectrograms, even though we have these challenges for training our variational autoencoder. Now, something I want you to match between what we have talked before and with the audio. So with audio, we can create condition generation as well. In our case, the prompt could be the artist, the genre, or the mood, and generate some audio based on this, condition on these inputs. But it could be autonomous generation, in which we have this P of X, this distribution in which we have nothing, but we sample random point, and then we create some audio. Or the continuation generation, in which we condition based on a seed, so more audio. Audio could be the label, the condition, the Y, and generate audio based on that. Questions to this point? I'm fast. Okay. No questions. Anything? Any comment, curiosity? Because we have time. Okay. So let's talk about then the autoencoder. The vanilla normal autoencoder. Do you know what we say vanilla? You know this word? Okay. Okay. You know it. Oh, vanilla means normal, standard. And it's because, I don't know, at least in the US, every time that you ask for an ice cream, it's vanilla. So it's the standard. So this is a standard encoder, normal encoder. Okay. So an autoencoder it's a model that we can use to do some dimensionality reduction. What we want to do is, based on some big data X, generate some small data set that condenses all the important information of X, so we retain it here and we can use it in the future to regenerate this data. So we are compressing, we are encoding. This is why it's called autoencoder. It has a step in which we have encoding. I would like to recap. You said you didn't know about PCA. I'm going to recap a bit about PCA. So we have here X that belongs to real space of size T. Okay. And we are going to encode this X. So we are going to apply some transformation matrix, okay, to generate the set. So we input X, transformation, set. And in an autoencoder, and that's why it's called autoencoder, we want to decode the information. In PCA as well, in principal component analysis. So based on this data, we transform the transposed version, so the opposite, to X. And we put a hat, because this X, even though we want it to be exactly the same, it's never going to be the same, because here we have a very small vector. So this is big, this is small. And the PCA is that one that when we want to reconstruct. Let me check. Yeah. So if I substitute, we transform, then we transform back, and we have the information we had at the beginning. More or less. More or less. Okay. So in PCA, this should be 1. No information is lost. Okay. But in the autoencoder, this is deep, so we can have layers. And this is non-linear. Because we apply ReLU to the neurons. Does it make sense to everybody? This is what we want to do. But why? I mean, why would I like to do this? Well, because if I can compute this, if I can train a neural network that is able to minimize this difference, so they are equal, they are the same, then I can do a lot of funny stuff. But important information is going to be condensed here in this set. Is it clear? So let's repeat it. We have our autoencoder, encoder, decoder. This vector in the middle, I haven't said it, but it's called the latent space or the bottleneck. Both are correct. And then we want to minimize this function. So the difference between the predicted value of the data and the data, in order to have in the middle some relevant information. What is an ideal autoencoder? The one that is sensitive enough to reconstruct the data, but insensitive enough not to overfit. Because what we want to do is things like this one. This is an autoencoder in which I have inputted some spectrogram. It has 5 layers, the small latent space in the center, 5 layers transposed, and the same spectrogram. Once this is trained, I can drop the encoder. I don't need it for anything. And then I can use where it's located, where this latent space, this small vector, is equivalent to others. So it's closer. It's numerically, if we have 1 and 2 in one for x1, and if we have for x2 1.1 and 2.1, these are very close, so these are very similar, then I can tell that if that means, for example, rock music, I can clusterize. I can do some clustering, some grouping. I can tell that the numbers that are 1 here or close to 1 and 2 here or close to 2 are rock music, because then I can decode it and listen to it. Is that okay? Is that clear? It was a difficult idea. Did you catch it? Yeah. Or I can do the opposite and, I can add some noise to the input data. I don't know if you can see it, but it's noisy, okay? Some white noise added to the input data. And I can train it with clean data in the end. So this difference, what we try to minimize is we try to find how to denoise signals. So in the future, when we have noise, real noise in some signal, we can input it into this neural network and we will output a clean signal. Or if we have an impairment, that is some missing data, then we can use it to reconstruct that data. So that's why we want to have the same input and the same output in the autoencoder, because some applications are very interesting and they're very useful in the end. This is, again, a comparison between the principal component analysis, that is the dimensionality reduction, okay, and the autoencoder. While this one needs to be linear, so it can only catch linear dependencies over our data, this can be nonlinear. So we can catch the non-linearities of the data and in the end be able to clusterize, for example, this data in a more efficient way, in a more accurate way in the end. Because with linear transformations, we couldn't be able to do it. We can't do it. It has to be nonlinear for this data, at least. And with this, we can do it. Okay. And usually, in this vector, I said this is a vector. So it has a couple of dimensions. It could be one number, but it could be also 20, as much as you want. It needs to be quite smaller. So okay, because it doesn't make any sense if it's not smaller, right? If we visualize it, this is, do you know MNIST dataset, handwritten digits? If we input MNIST in something like this, what we may find in the latent space is these clusters, these points. Each of these points is a different handwritten number. And one of the characteristics of the latent space is that they usually tend to clusterize So this is the same idea as this one. For example, this is purple, so number 0. Number 0, all of them look alike, right? So all of them are going to fall into the latent space with closer numbers. So this is the same idea. And then we can see it. We can observe the latent space and learn things out of the latent space. So we can do feature interpretation of the data. That's another important thing. But the autoencoder, and that's why we are going to talk about variational autoencoder, has some problems. The first problem is that there's no symmetry around the center. So that could be problematic in the sense that it's more difficult to understand what is going on, why it's not center, why this one is that far from this one, or why this one is in the center. We don't really know. This is a problem. Second, we have blank spaces. So for example, here, what number should be here? No number, but what is in there? I have no idea. I need a point in here to know, but we don't have any point. So what is that? Gaps, we don't want gaps, white spaces in the latent space because lack of information. And then another thing is that some clusters are higher than the others. Why? I don't know, but I would like to know. So these 3 problems are actually small problems. It doesn't matter. But the big problem is that there is no way to sample new data from here. So everything that I said at the beginning, we want to model the distribution, we want to sample generate new data. We can't do it with an autoencoder because this is deterministic. Every time that I input one X, I'm going to have the same outputs. So there is no point no point on taking new data here to generate data in the decoder. There's no point because we don't know what is in the blank spaces because this is not a continuous space. We just have information of the points, but we can't get information of the blank spaces where novel information is. Okay, so we need to make this latent space continuous, like a distribution. That's why you have to link that idea with what we have said so far in the class. Any question? Okay. Is it recording? Okay. So now, quick recap. We have the autoencoder. We want to have a smaller version of the input data, reconstruct the same data. Of course, it's not going to be the same, but we are going to minimize it as much as we can. This is deterministic. So we have information on the point based on some input data, but we don't know about anything in the blank spaces. And then we want to have a way to fill all this lacking information in the latent space. So variational autoencoders. This first slide is for you to have. This is not specifically for the variational autoencoders, but if you remember the taxonomy, as said, we have the generative models, and then the ones that we could compute explicitly the density function. This is how we usually formalize mathematically the idea of using a neural network or of maximizing the likelihood of the input data. So we have the density function of X, and we want to have some neural network to model this density function. This is what I said at the beginning of the class. F, the neural network, that is going to have the same input data, training data, and some W weight matrix, that is the weight of the neural network. And what we want to do is to maximize the likelihood of every single point, every single point in our training data set. And we are going to assume that every single point is independent. So the probability distribution, the density function of this data set is the multiplication of the independent points. Do I repeat? Or was it clear? Probability density function of X, we want to model the density function of our input data using a neural network F that is going to use the input data, training data, to change their weights. So it outputs our density function, and we are going to assume that for every single data point in our training data set, they are independent within each other. So the probability is the multiplication of every point. We don't like to work with products. We take the logarithm, so it's a sum. And we substitute for the neural network. General idea of what we want to do. This is how, when we want to compute some explicit density function with a neural network, this notation, this idea. And this is the last hard maths that we are going to use today. Almost. So, the variational autoencoder. We have our normal autoencoder here, okay? And we want this to be a distribution, a probability distribution. So what we are going to do is, instead of having this vector, we are going to split it in two, and we are going to compute some mean vector and some standard deviation vector that are going to be the mean and the standard deviation of some distribution that is going to live in this latent space. And because we are computing a mean and the standard deviation, we are going to say that our distribution is going to be Gaussian. If you remember Gaussian distribution, we have mu and sigma, mean, standard deviation. This depends, okay? It could be, if it's a multivariate distribution, that is more than one dimension, this is sigma, so this is covariance matrix. And a very important thing is that this covariance matrix is diagonal. So it's the same as having one vector. That's why we usually say it's sigma. Because if it's diagonal, it means that we have data and zeros. So we just need to, this is a vector, sigma. Okay? So the idea is that we are going to force our encoder to learn some mu and some sigma. And this mu and this sigma is the one that we are going to use to create a probability distribution that is going to be the one that is going to, I mean, we are going to have a distribution in the middle. That's the idea of what we want to do. Is that clear? This is the way we can have a probability distribution in the middle, by computing mean, standard deviation, and then wrap it into some known distribution, normal, Gaussian. Okay? Just to, it's important for you to understand that this is a simplification of the problem. That we are not going to get into the hard mathematical details of the implications that this has. But as a way to understand it, as a simplification of the problem, this is perfect. This is the idea, what we want to understand today. Okay? But now that we have mu and sigma, and we can wrap it in a probability function, normal, then to create some vector that is going to be the latent space, because in the end we need to have something that, like we have here, and this is a vector, right? We need to sample this distribution, get a sample based on this mean and sigma, get one sample, and this sample is going to be the set. Okay? Now, think about what I said before. This was stochastic. So for one x, I will always have the same set, and I will always have the same reconstruction. But now it's not stochastic anymore. It's a probability. So now I get x, I compute mid and sigma, I sample. And every time that I sample, it's going to be different because it's a distribution, it's a probability. And now this is going to be different. That means that when we had, is it okay if I erase? How do you say that? Erase? That means that when we had our lattice space, and for x1 we have 1 point in a normal autoencoder, for x1 now we are going to have a cloud, a bubble, a volume, some space. So we are filling the latent space. Now the blank point, the blank gaps that we had in the latent space, there are no blank gaps anymore because we have distributions. And now it's filled. That's why we wanted to convert our encoder to the variational autoencoder, because now we can fill the latent space. Is that idea clear? Because it's quite complex. Okay. This is the same idea, but now it's drawn. When we had a number 6 in the MNIST dataset, in the normal autoencoder, this was a point, and now it's a distribution, and it's Gaussian, as I said, Gaussian. It could be anyone, but we usually use Gaussian because it's simple, it's normal. And when we have more data, this is going to be filling the latent space with distribution. But there's a problem. Always, there's always a problem. And the problem now is that whenever we want to train a neural network, you know the backpropagation algorithm, right? That is, we compute the error and we flow to the beginning, computing the gradients and modifying the weights based on the gradients, but it needs to flow. So everything needs to be differentiable and connected. But what is this? Sampling? There is no gradients in sampling. That's taking a point from a distribution. How can we compute the gradients to the end to train this variational autoencoder? That's a very difficult question, but we can apply some trick. The trick is that this is what we had, right? The variational autoencoder. We can't do it because we need to sample here. But what if I tell you that we are going to sample from a known distribution? Known distribution could be a standard normal distribution. And we characterize this distribution. We take a sample in which we include the parameters mu and sigma in the way that we usually do that. Like when we want to move this distribution that is in this 0 and has a form like this, what we can do is sum mu and multiply by sigma. And now this distribution could be anywhere and could have any shape. But the sample, we take the sample from here. So we take the sample, and then we sum mu, and then we multiply by sigma, and now the sample is anywhere in the space. So if we take the sample from something that we know, this is out of the flow, because we need to flow through sigma and through mu. But what I'm saying is that we are going to sample here and sum this and multiply by this, the opposite. So the flow, this can flow the gradients. Is that clear? Because this is a bit difficult to understand. We sample here, which is out. Sample any number here, it could be 0.5. And because we have mu that is trained, mu is 6, and sigma is 2, then we sum, so 0, 6. And this is the number that we have in our Latin space. Questions? It's a trick. We are tricking the system. Let me check if I have some other image that could be. No. The idea is that we need to move this out of this connection, but we need a Latin space, which is this set that we need to have here. What can we do? We can sample from a known distribution, sum mu, and multiply by sigma. And this is something that, believe me, you can do it with a distribution, and you can do it with a sample. That this sample that we have sampled from the known distribution and applied this computation is equivalent to this sampling from directly this distribution. It's equivalent because it's what we said, it was a normal distribution, and this known distribution is also normal. Is it clear? This is a reparameterization trick.
So it's that you can train.
Now you can train the neural network. I know this could be a bit more tough to understand, but let's dig in our knowledge. We will continue with this. We can, if you have any questions during the class, we can solve it at the end. Okay. So now that we can train the variational autoencoder, what happens if we use this loss function, like the one that we had in the normal autoencoder? So what is going to happen is that if we just apply a reconstruction error, then most probably this is going to overfit in the sense that it's going to ignore the standard deviation, it's going to remove it, and it's going to apply only mu. Because there's nothing that wants this model to be probabilistic. It's actually easier for this model to be deterministic. So it's going to kill the variance. It's going to let the mu just pass like a normal layer, and this is going to become a normal autoencoder. So how do we force the variational autoencoder to learn a distribution? We need to add some regularization, KL. KL stands for Kullback-Leibler divergence. Okay. Do you know about Kullback-Leibler divergence? It's a mathematical, it's not algorithm, it's how do you call that? An operation in which we are going to measure how similar two distributions are. So we are going to compute the Kullback-Leibler divergence of this distribution with this distribution. So we force our model to be similar to this distribution, that is, to any distribution, but at least it's a distribution. So now it's not only learning how to reconstruct the output, but it's also learning how to have some distribution in the middle. If we apply this regularization, because this regularization is forcing to be equal to a distribution, to be similar to a distribution. It's called Kullback-Leibler divergence because it's a similarity matrix of two distributions, how similar they are or how different they are. But we want them to be similar to this one. So we are forcing this autoencoder to have some probability distribution in the middle. And also we are forcing it to reconstruct the output. I know this is a difficult concept, and you need to have an equation. Okay, then believe me. Because if we didn't have this, then most probably this is going to kill the variance. There is no motivation for the autoencoder to become probabilistic. We need to force it to try to be close to a distribution. That way, we force it to be probabilistic. This is the mathematical. This is what the Kullback-Leibler divergence looks like with the distribution that we are learning here and the distribution that we know. And why are we using 0, 1? That could be a question. Why not any other? Because of this, because it has a closed form. Closed form means that we have parameters and they are very simple. This is just sum sigma square, mu square, sigma square again. This is closed. So we can code it. We have sigma, it's here. We have mu, it's here. Now we can code it. 1 plus logarithm in a minute. Okay, that's why we use this distribution, because this is the result of the Kullback-Leibler divergence, and it's closed. It could be any other thing, but maybe it's more difficult to compute. This is the entropy between the two distributions. You can compute it, integrals, but if you compute this one, you have this result. If you change this one, it could be super difficult. Okay, that's why. There was a paper that included some hyperparameter beta. This is because nothing tells us that this error, the reconstruction error, and the Kullback-Leibler divergence are in the same ratio. I mean, this one could be massive, and this one could be very small, and then the neural network is going to try to reduce only this one, and it's going to not care about this one, or the opposite. So we include a hyperparameter, so we balanced both error. So the neural network is minimizing both at the same time. That's why. And this is proven to work. And we are use it in the next day when we code our variational autoencoder. So this is another way to see it. And it's called, like, we have forces. This is the latent space. As I told you, now it's not a point, it's a bubble, because it's some distribution, some points that we sample here. And this one is a different image, and this one is a different image. And the reconstruction error is pushing everything away. Because if this is now not a point, but a volume, how can we reconstruct something that it's intertangled, it's mixed? If this one comes from a 101 and this one comes from a 9, if they are entangled, there's no way to reconstruct back. They are entangled. So the way that the neural network is going to train is that they're going to push them away until the infinity. That's where the minimum is. And we don't want anything in infinity because that's broken. That's why the regularization of the Kullback-Leibler is introducing a force to the center. That is, if this is the same formula I showed before, this one has a minimum in 0. So the minimum is in 0, and the minimum of the other one is in infinity. They're pushing on opposite directions, so we are going to reach equilibrium, which is this purple bubble. And this term is the one that is going to force not to kill the variance, because it has a minimum in 1. So if the variance has its minimum in 1, this is not going to be killed. This is not going to be 0, because it has a minimum in 1. And that's the force that we will have here. So a variational autoencoder latent space is going to look like this. Not this is going to be the center. This is going to be packed. All the bubbles tend to be the same size. Do you remember all the problems I told you of the normal autoencoder? Bah, it's saved. It's solved. That's it. That's the way we do it. And most importantly, oh look, yeah. So the normal and the other one. This one, every cluster is the same size. It's centered in zero. The white spaces, there are less white spaces. It's more packed. And the most important thing, now this is a probability function. So these are points, but in reality, these are bubbles. So now in the white spaces, there is no white spaces. And we can pick one point, one number in the latent space, any number, and create a new data. So now we can sample this probabilistic latent space, send it through the decoder, and create a completely novel data point. A completely novel image, a completely novel audio, anything but new, based on the training dataset, but new. And this is what is going on these days in artificial intelligence. Now you understand why. And everything is related to probabilistic algorithms. And that's all I wanted to tell you today. Because I think that, yeah. Well, it says on Thursday, on Tuesday, we are going to code this. So if you can bring your laptop. Wait. We are not finished. But bring your laptop on Tuesday, and yeah, we will code this variational autoencoder on PyTorch. Okay. Questions, please. Let me show you. This is a different latent space. This is not a latent space of a variational autoencoder, but it's illustrative. You can see, because we have seen two-dimensional latent spaces, but it could be three-dimensional. And this is words. So words that its meaning it's closer, they are going to be closer in the latent space as well. Okay. Or, of course, stable diffusion. We can condition this model on a prompt, and we can generate images based on this prompt, completely new images. This is amazing. I mean, we are used to it, but it was created by artificial intelligence, not a human. Or this one is my work in. I mean, this is something because I'm taking a PhD. This is an illustrative application that I created. This is a latent space, but trained with audio. These are 3 audios. We can listen to them. Sorry. Wait. Okay, this is a stroke over metal and wood and wood. And now we can sample from anywhere in the latent space and create new audio. Oh, sorry. This is new. I don't know why it's working so bad. Sorry, it should work better, but it's just stuck. New, completely new. It should work faster, okay? I don't know what's going on. But that's the idea. We can create audio. And this is what we are going to do. We are not going to upload it to the website, but we are going to do it on local. That's all. Thank you for coming. I hope you learned a lot. And if you have any question, you can send me an email or reach me in my laboratory. Thank you.